Dear students, welcome to lecture 12. So today we are going to study about another heterocyclic aromatic compound, that is pyrrole. So pyrrole is a heterocyclic compound which contains a nitrogen atom substituted in a 5-membered cyclic ring structure. It has a melting point of -23 degrees Celsius and it boils at around 130 degrees Celsius. So mostly it is a liquid at room temperature which develops colors gradually. But pyrrole is slightly different from pyridine because the nitrogen lone pair is part of the pi electron cloud which is perpendicular to the plane of the ring. This we can see by comparing these structures of pyridine and pyrrole. In pyridine we have seen that the lone pair is in the plane of the ring like this and it is occupying an sp2 hybridized orbital and it is not part of the pi cloud. Therefore this is available for any incoming acids to bond with. Therefore pyridine is more basic. But if we take a closer look at the structure of the pyrrole, we find that the lone pair is perpendicular to the plane of the ring and it participates in the pi electron cloud, and therefore pyrrole is also aromatic because it has 6 electrons in this pi electron cloud, has pyridine. It also has 6 electrons in the pi cloud, but those doesn't include the lone pair. In the case of pyrrole, lone pair is part of the pi cloud. Therefore, it is less basic. And we can find that we can write resonance structures which contribute to the aromaticity of the pyrrole, and it has an average resonance stabilization energy or aromatic stabilization of energy of around 22 kilocalories per mole. This can be explained by accounting for the resonance hybrid structures in which when the charge is separated, the structure is relatively unstable, and when the charge is located on atoms, it is slightly more stable. And because of all these reasons, pyrrole is a weak base and it has a pKa of 13.6. Now let us turn to the synthesis of pyrroles. Pyrrole itself can be prepared from furan by passing furan gas and ammonia over alumina at high temperatures. Under these conditions, a reaction will take place, will lose water and form the pyrrole. But there are better methods of synthesizing substituted pyrroles. One of these method is known as Paul-Knorr synthesis of pyrrole, in which dicarbonyl compounds are treated with ammonia and heated. They form 2,5-dimethyl pyrrole derivative. So if 2,5-hexadione is reacted with ammonia at high temperatures, it gives 2,5-dimethyl pyrrole. Paul-Knorr synthesis can be modified, and we can use amino acid derivatives and react them directly with the ethyl 3-oxobutanoate under acidic conditions. And if we heat this mixture, we'll get the substituted pyrrole derivatives easily. Similarly, if we use the methyl 3-amino-butanoate and allow it to react with chloroacetone, then it will give us the substituted pyrrole derivative. Thus we can see that different substitution patterns can be incorporated in the pyrrole, and there are further methods of synthesizing pyrrole, and these include passing acetylene and ammonia gas over high temperatures over catalyst to give you the pyrrole. But another method, well-known method, is the use of succinamide. When this is treated with zinc dust, which is a reducing agent, it generates pyrrole. Similarly, fused pyrrole derivatives can be prepared by a method popularly known as Fischer-Indol synthesis. In this, the phenyl hydrazines are treated with ketones, and you get the corresponding acetophenone phenyl hydrazone, which is then reduced to give 2-phenyl indole. Now, mechanism for this Fischer-Indol synthesis has been discussed a lot in the literature, and the accepted mechanism goes like this: that first the phenyl hydrazone is protonated and intramolecular electrophilic aromatic substitution takes place, where this carbon adds to the aromatic ring, nitrogen-nitrogen bond breaks apart, and this is followed by aromatization of this benzene ring to give us that intermediate, which will further cyclize because of the nucleophilicity of the nitrogen to give us another intermediate, which again loses a proton from this newly formed 5-membered ring to give us the 2-phenyl 1H indole, and ammonia is lost in the reaction mixture because of the aromatizing driving force. Now let us turn to the reactions of pyrrole. The 5-membered heterocyclic aromatic rings, as expected, undergo electrophilic aromatic substitution reactions, and these electrophilic aromatic substitution reactions are faster than those for benzene, and this is because the pyrrole and other 5-membered heterocycles can accommodate a positive charge by sharing the lone pair of electrons with ring carbon atoms. That we can see here. When the electrophile is coming with a positive charge, the positive charge is delocalized within the 5-membered ring, and it can be easily further stabilized by the lone pair of the nitrogen and form a highly stabilized intercontributing structure. Even in the case of C3 substitution, the similar intermediates are possible in which the nitrogen lone pair is helping to stabilize the positively charged intermediate. Then another well-known reactions of pyroles is the ring expansion. When chloroform is treated under basic conditions, dichlorocarbene is formed. This, being an electrophile, adds to the double bond of the pyrrole, and then rearrangement in the molecular framework takes place to give you a pyridine derivative, and this is known as a ring expansion of pyrrole. Can you propose a mechanism for this ring expansion using the following hint? Our next lecture will be on furan. So see you then. Thank you.